Hi students, we're going to talk today about logarithmic functions. Now logarithms or logs, these can be kind of tricky for students and kind of scary, but don't let them scare you. Here's how they came about. They allow us to take an equation like this, c equals b, our base, raised to the power of a, and if we want to solve it for a, well, what do? That's the whole reason why logarithms were developed. Also, logarithms are used to express quantities that vary widely in terms of their size, either very small quantities or very big quantities. You'll find that, for example, if you live in California, like I do, we have earthquakes here, and earthquakes are actually on the logarithmic scale. So that Richter scale is logarithmic because the numbers can be very big or very small. There's lots of other applications of logarithms in science and technology that are used. The first thing I want to talk to you about here is this equation that I have. And it's going to help us solve what I am erasing right now. If we have something like an exponential expression, b to the a is equal to c. We can write it as a logarithm. So we have, this is a really important formula per se, or property that you'll want to remember. This double arrow means that if and only if, or meaning that it could go both directions. If you start with an exponential expression, you could write it as a logarithm. If you start with a logarithmic expression, you could write it in exponential form. So it just depends on the type of problem you're going to use as to what form you're going to write the problems in. As for logarithms, we have two kinds. We have a common log, which is log base 10. So if you look over here, this is log base b. So notice how the base here in the exponential form was the base of the expression. Well, the base goes down here after the word log, and then what comes after it? What's on the other side of the equal sign? The c, or you can call it y if you wanted, equals the exponent a. All right. So when we have a logarithm base 10, we can just write that as log. That's all it is. If we show it just as log, we assume, and it implies that the base is 10. If we have something called a natural log, and that's log base e, that Euler number, well, that can be written as ln, logarithm natural. Some people call it ln. That's okay, but that's really what it means, is that you're taking the natural log. You're assuming that the base, in this case, is e. Let's review some of the properties of logarithms before we work on some examples. So number one here, we have log base b of m times n. What happens when you have a product that you're taking the logarithm of to any base? You divide it up into two logarithms and add them, or take the sum of the two logarithms. If you have a division that you are taking the logarithm of this quantity that's being divided, you would subtract the individual logarithms. So notice log base b of m divided by n is going to be the log base b of m minus the log base b of the number or the quantity in the denominator, in this case n. Property number 3 is a very useful property, so keep this one close and handy. So log base b of m raised to the n power, what we can do with that n power is it can come and become a multiplier. So it comes down in front of the expression, the logarithmic expression, n times log base b of m. Very, very handy. These last two, numbers 4 and 5, I'm going to show you and illustrate why they're true by using our expression up here, or our equality of equations, that our logarithm is equivalent to an exponential expression. So if we have log base b of 1 is equal to 0, so it's in this form. Notice that c is 1 and a is 0. So if we write it with our base b raised to the a power b to the 0, is that equal to 1? It is. Number 5 here, log base b of b is equal to 1. So once again, we're going to write this logarithmic expression in exponential form. So we're going to take the exponent, this b, and raise it to the first power. And is that equal to what's next to the logarithm, which in this case we're calling it b? Absolutely. B to the first is indeed equal to b. So here's two more properties that we want to talk about. And how they're handy is if you have an expression, that has ln of x in it, well, think of it that if you raise that quantity to the power of e raised to that quantity, it becomes the exponent of the e, then it kind of undoes the ln. The e and the ln go away, and we're just equal to x here. Also, if you have an exponential expression, something with e to the x, the natural log, applying that to both sides of an equation, that will just undo the e here, and that leaves you x. These are two really handy properties to understand fully because they will help you solve exponential and logarithmic equations. Let's try some examples. Let's solve the equation 2e raised to the x plus 2 power is equal to 5. So the first thing we want to do here is divide out that 2 from both sides, on the left and on the right. So we're left with e to the x plus 2 on the left side is equal to 5/2, or 5/2 on the right side of this equation. Now, how do we undo that e? Think about what I said earlier. And again, the 7 properties, what I recommend you do is you have them all written on a separate piece of paper. And every time you go to work a problem, put them next to your problem and review them, because it'll start to click easier for you having all the properties together in one place. So what do we have here? An exponential function. We want to undo it by applying a natural log to both sides. So I'm going to apply to the left side a natural log of e to the x plus 2 is equal to the natural log of 5/2, or 2.5. I can keep it as a fraction, write it as a decimal, write it as a mixed number. That's not so helpful, I think, with the calculator. I think a fraction or decimal is usually easier. So once again here, we're applying the natural log to both sides. That's going to undo the e and leave me with x plus 2 is equal to the natural log of 5/2. I'm not done yet because I need to solve for x. So subtracting 2 from both sides will give me the natural log of 5/2 minus 2. But there's another way you can write this. Again, going back to our properties. What do we do when we're taking the logarithm, either a common log or a natural log, of a division? Well, we split it up so that x can be equal to natural log of 5 minus natural log of 2 minus 2. We leave the minus 2. It's not part of the logarithm because we just subtracted it from both sides at this point. For the next problem, we're going to write a string of logarithms as a single logarithm, so just as one. So what we want to do, going from left to right, we want to simplify these logarithms. So we have this 1/2 and this 1/3 here. That would be the first thing that I would do, I would pay attention to before I go left to right. Because remember, we have the property that if we have an exponent on the variable here, or whatever follows the logarithm, we can bring that down and it's a multiplier, like you see here. So let's go ahead and just rewrite these so that the exponents now are, we have natural log of x to the 1/2 power right there, plus natural log of y minus natural log of z raised to the 1/3 power. That'll make it a little easier for us to combine our logarithms. So let's now look at the first two here, the first two terms. So when we have addition, what do we do with the values? We multiply them. So we'll have here natural log of 3x to the 1/2. Okay. And because addition is commutative, we could do them in any order and we would get the same answer. What I'm going to do here is take care of them pair by pair, and then we'll put them together because we still have this addition down here. So what do we do when we have a subtraction? Well, we'll have a natural log. Remember, the subtraction between the two logarithm terms means that we divide both values that follow the logarithm. So y divided by z to the 1/3. Okay. Now we have, once again, a sum. Let me bring this a little bit higher up here. We're going to take the product of these two quantities here. So we'll have a natural log of 3x to the 1/2 times y divided by z to the 1/3. We can express it like this, or we can express it with radicals. It will depend on what your instructor wants you to show. So this would become 3y times the square root of x divided by the cube root of z. Remember, the 1/2 power means a square root. So x to the 1/2 is equal to the square root of x. Z to the 1/3 is equal to the cube root of z. Hope this helps you. Bye, students. Let's look at this next example, number 3. We're going to expand the expression natural log of the square root of x plus 1 divided by x squared plus 1. So one thing I want to mention before we move on and work this problem is this could have said log with a base. It doesn't matter. We can apply the rules for logarithms, our properties, whether it says ln or log. So we see a division here. What do we want to do? We want to break this up into two logarithms, in this case two natural logarithms, square root of x plus 1, ln of the square root of x plus 1, and we want to subtract these two logarithms. And I'm going to show this in parentheses just because I am taking the logarithm of this quantity, the whole thing. So what else can I do here? Well, maybe you want to think about, can you express the square root of x plus 1 as x plus 1 to the 1/2 power. Because then what will happen here, the 1/2 will come down and become the multiplier of this logarithm. So we'll have 1/2 times the natural log of x plus 1 minus the natural log of x squared plus 1. Now be careful, because we can't do anything further here. It's going to feel like you should be separating these out, but that's not what our property says. Remember, our properties say that if we have a product of two quantities that we're taking the logarithm of, that we would then express them as two individual logarithms, the sum of those logarithms. Or if we have a division like we had here for this problem, it wasn't the natural log of this quantity divided by the natural log. It was the natural log of this whole division, this quotient. So be careful, because it's going to be tricky, and it could be easy to forget that this is as far as we go here. We cannot simplify that any further. Bye, students. So now let's look at problem 4. We want to solve this equation. 2e to the negative 0.2t minus 4 is equal to 6. So the first thing I want to do is I want to try to get to that e, the term with e in it, and I want to undo everything else around it. So I have to first add 4 to both sides. So I'll have 2e to the negative 0.2t is equal to 6 plus 4, which is 10. And then undo this multiplication of 2 by dividing both sides by 2. So 10 divided by 2 is equal to 5, and I'm left with, on the left side, e to the negative 0.2t. So what am I trying to solve for? I'm trying to solve for t. I'm trying to get something down here that says t equals a quantity. How do I get to that t? Well, I want to undo this e. And remember, what do? We apply the natural logarithm to both sides. So natural log of e to the negative 0.2t is equal to natural log of 5. And by the way, when you see e as the exponential base here, the Euler's number, remember that natural log is log base e, so we have to use ln. We can't use log here to undo this e. That doesn't work. So it does work here, though, because the natural log of that has a base e, and there's base e here, that will undo that e, and we're left with negative 0.2t is equal to ln of 5, natural log of 5. And now to solve for t, we simply divide both sides by negative 0.2. And we have that t is equal to natural log of 5 divided by negative 0.2. For this problem, because I did not state to approximate the answer, I would leave it in this form. Showing the natural log of 5 is actually an exact answer, because it's saying if you put this directly into the calculator, you will get a value. It may be a non-terminating decimal. It's very likely that this would be that way. We could, when we're solving problems, we usually leave it in exact form, because that is the only number that when you replace it with t in your equation here, that would result in the left side of this equation being equal to 6. Since the right side is equal to 6, that's what we're trying to do, is find that equality here with this equation. I hope this helps you. Bye, students.